All right, so yeah, thanks for sticking around. And I think there are more speakers than people in the audience today. But right, okay, so let's move to the big question. So it's about the continental growth, and as you can see here, there is a lot of controversy. So that figure is plotted the volume of the continental crust, which is normalized to the present-day volume of the crust, and as a function of time. So on the right-hand side is the present, and that's the Earth formation. And as you can see here, there are many, many different models, and some of them pretend that most of the crust were formed early in Earth's history. Some others believe that the continental growth kicked after the Archean or something like that. So, I mean, there is still a big question mark on that figure, and what I'm going to try today and give you is to give you some more insights using the sedimentary record, because, well, that's the theme of the session. So, using two different approaches. So, one is based on the neodymium isotopes in shales, which are continental sediments, for those who don't know that. And the second approach is based on the combination of hafnium, uranium, lead, and oxygen isotopes in detrital zircons. Okay, so let's move to the first approach. And so this is not new. So everything is about recycling here. So what we did here is we exhumated a paper from the 80s by Allègre and Rousseau. And, well, all the good stuff was done in the 80s, and this is a good example. So what I did here is just using the neodymium isotope composition of shales from Australia. So those shales have a range of deposition ages. And they have that really nice correlation here, so that curve which shows basically a linear decrease, and that curve fades out toward the present day. And with that kind of curve, you can directly plot a continental growth curve. So this is the green curve here. So the scale is reversed. So this is the Earth formation now, and the present is on the left-hand side. But, well, there is still an issue. This is not the true continental growth curve. So that curve is biased somehow because we are analyzing sediments. And so the main question here is to try and understand what happens when you switch from the magmatic to the sedimentary record. And this is a really simple representation of the model that Allègre and Rousseau used. They used an erosion parameter, which is called K. And so this is the expression. And in their model, they are just assumed that at any stage of its evolution, the continental crust was formed by two different blocks. So one block was composed by the juvenile crust, which is the green stuff here, and the other one is the pre-existing crust, okay? And when you start and erode that bulk continental crust, you are going to have more sediments coming from the juvenile crust, because we know that they are formed in young mountain belts, like here, and there is more relief, and which means that the denudation rates are more important. Therefore, in your sediment, you will have a larger proportion of sediments coming from the juvenile crust, and the mean age of the average age of your sediment is going to be younger. So this is what is expressed here through that erosion parameter K, which is basically the proportion of the juvenile crust over the pre-existing crust in a sediment over the proportion of the young crust to the pre-existing crust in the source. So what does it do in terms of the continental growth curves? So we are back to our neodymium in shales curve in green, and those are different curves taking different values for that erosion parameter. At the time the paper was written, Allègre and Rousseau assumed that the value of K must be between 2 and 3, so those are the two red curves here. But actually at this stage, it was not based on the proper measurement of that parameter. And as you can see here, the greater the value of K, and the more crust was present early in Earth's history. So, is there a way that we can try and measure that parameter? The answer is yes, and we found a really simple system which is pretty similar to the model of Allègre and Rousseau. So the studied area is located in in the south-western part of Australia. So this is the Franklin River, which is draining two continental blocks. One is the Archean Eelgan, and the second one, which is younger, is the Proterozoic Albany-Fraser orogen. So this is the map of the river. So we've taken a range of samples across the river. And from those observations, so we were able to determine the parameter K. So this is a pretty busy figure, so I'm going to try and break it down for you. So first, the K parameter in that context reflects the proportion of the Albany-Fraser to the Eelgan in your sediment over the proportion of the Albany-Fraser to the Eelgan in the source. The proportion in the source on that figure, which is basically as a function of the distance to the coast. So on the right-hand side is the Eelgan craton, and the left-hand side is the Albany-Fraser origin. And that vertical dashed line is the boundary between the two blocks, okay? So if you take the proportion on the map, which is basically taken from the different areas of the catchment of your sediments, you see that you have 100% of Eelgan, of course, in the Eelgan section, and then the proportion of Eelgan slowly decreases. So that's the proportion in the source. And then using a combined approach with different isotope systems, so uranium-lead, hafnium, and neodymium isotopes, we were able to determine the proportion of the Eelgan in the sediment this time, and it's different from the source. So this is what you can see in that gray envelope curve, and the deviation only represents the difference between the two methods that we used. And the greater the deviation to the source, the greater the parameter K is. And what you can see here is that parameter increases with the river profile, and there is an important increase after you passed an inflection point in the river profile. So when the topographic relief becomes higher, the value of K is greater as well. Okay, what is missing? Right, that's okay. So the next question now is, well, we have demonstrated that there is really large range of variation for that K parameter, but the problem now is to try and determine a global value for that parameter. So this is still a work in progress. We don't have any answer, but we have a couple of guesses. So one, if you take just a compilation of the hafnium isotope in zircon as a function of their crystallization ages. And if you do, so this is the data from Belousov et al. That many people have used recently. And if you just try and plot the running average of the data, you see that that blue curve has a way more enriched isotope composition compared to the juvenile crust, for instance. So that means that the crystal record on average is dominated by the remelting of pre-existing crust. And we know that remelting occurs usually in areas where the crust is thicker, and thicker crust most probably means high topographic relief, and therefore a high value of K. So we are expecting a high value of K, and those are the implications in terms of the different parameters we have measured in the Franklin River. So for low values, you are forming up to 50% of the present-day volume of the continental crust by 3 billion years ago. And for higher values, you form up to 75% of the present-day volume. And the important point here is as soon as you are reaching high value of Ks, you have an inflection point of that continental growth curve. So there are important implications that I will try and discuss later on. The second approach is based on the zircon record, so I'm going to be quick on this one. Many people have discussed those diagrams, so this is just a compilation of plots for the Australian continent. You might want to take a different database based on different continent or something worldwide. But the point here is if you take the detrital record or the magmatic record, you're going to end up with a series of peaks and troughs. And they are pretty similar, and they are associated to the supercontinent cycles. Some people interpret those peaks and trophies as an increase in terms of the magma production and perhaps the growth of the continental crust. Some others believe that it might just be a preservation issue. I'm not going to discuss that matter here. But if you compare those curves, those plots, with the distribution of the model ages in the zircons given by the hafnium isotopes, you end up with something which is actually more smooth, and the peaks and troughs disappear. Yes, but there is an issue, and everyone knows that. That issue is related to the interpretation of the model ages. So this is a nice example from Kemp and Cotter in Nature, 2006. And what they did is analyzing zircons from the Lachlan Fault Belt in Australia. They plotted the model ages for zircons with what we call mantle-like oxygen isotopes. So here they are lower than 6.5 per mil or something like that. And you see that those model ages are only showing a bimodal distribution with peaks at around 1.9 and 3.2 or 3 billion years ago. So which are supposed to represent 3 episodes of crust extraction. And then zircons with higher oxygen isotopes value plot just in between. So they are interpreted, in fact, as a mixture between old and young crust. So in that case, your model ages are not representative of any geological process. So the question now is, how can we get rid of the bias given by those hybrid model ages? So this was what we did recently. So this is a worldwide compilation for all the hafnium oxygen data available. And I'm not going to go into detail. Everything is in the paper. But what you can see here, if you plot just the model age of your different zircons with typical mantle-like and hybrid model ages, so mantle-like is green, hybrid model ages are on the gray histograms, then you end up with that relationship that actually shows there is a correlation between those hybrid model ages and those new crust model ages through time. And you can use that correlation to try and predict the proportion of those hybrid ages through time. And you can use especially that correlation in much larger databases for which you don't have oxygen isotopes. And what we chose here is a worldwide compilation for young sediments, because we believe that they are the less biased representation of the magmatic evolution of the crust. And when you combine those two, you end up with a continental growth curve, which is the blue curve here. And that shows actually a two-stage evolution of the crust. Stage one is a rapid increase of the volume of the continental crust from 4.5 or something to until 3 billion years ago. And at 3, you see an inflection in the curve that actually shows that the net growth rate of the continental crust is decreasing for a value of about 3 kilometers cubed a year to about 0.8. And if you still don't buy that those continental growth curves, so two different approaches, and here comes the third approach, paper recently published to Nature by Pujol et al. In 2013. Completely different methods. So now we are looking at argon isotopes, and again they end up with a continental growth curve that shows a large increase, an important increase of the volume of the crust within the first 1.5 billion years of Earth evolution, and still an inflection at around 3 billion years ago. So what about the implications now? We can somehow interpret that change in terms of the net growth rate of the continental crust as an increase of the recycling rate of the crust. And in that case, if you are increasing the recycling rate, you might need a different tectonic setting. And in that case, well, might it be the onset of subduction? Another argument here is a paper recently published by Sherry and Richardson, and that shows that sulfide inclusions in diamonds shows eclogitic signature only for 3 billion years ago. And again, it was interpreted as a large-scale onset of plate tectonics at 3 billion years ago. So implications, maybe before 3, at least on a really large scale. I'm not pretending there is no subduction before 3 billion years ago, but before 3, the main tectonic regime might be dominated by those vertical plume-like tectonics. And then from 3 billion years ago, we start with something which is pretty much similar to what we observe at the present day. So just jumping back to the conclusions now, we believe now that the continental growth occurs as a function of a two-stage model, something really simple. 60 to 70% of the present-day volume of the crust was most probably formed early in Earth's history by 3 billion years ago. The inflection in the growth curve at about 3 billion years ago can be interpreted as a decrease in terms of the growth rates. And as we know that today the rates of formation of the crust is about 3 kilometer cubes a year. And so we believe that that might be due to an important recycling of the crust, and therefore you need a tectonic process for that, which might be the onset of plate tectonics. And the work still to do now is to try and determine the global value for the parameter K, and perhaps see if we can also confirm the data we had for the zircon work. So that's still work in progress that people in St. Andrews are doing right now. Thanks for your attention.
Any questions?
Jeff?
Yeah, you show a considerable amount of Bristol growth prior to 4 billion years. Where's that in the record? Did they not produce many zircons, or those zircons have been destroyed, or what do you think about that?
Yeah, we don't have many zircons for that. I mean, that part is mostly related to those model ages, but we don't have many zircons with actually crystallization ages at this time. And well, I mean, to be fair, the model is anchored here at the beginning of Earth formation, but more and more people believe that the effect of some early meteorite bombardment may have destroyed all the crust. And I think my last thought about it is that you start actually growing the crust more at 4 billion years, something like that. But this may be for the next study. Stefan?
So where you've got usual argon.
Yeah.
Because I think there it's saying that by it's constraining actually early in the evolution that you can't. It suggests you can't have had much crust grow before 4 billion. Otherwise, the argon would have gotten into the atmosphere. So I think there's a little inconsistency with the large amounts of crust at, let's say, 4 billion, argon is saying no.
Well, it might be a question for them actually, but of course I do like the model because well, it's kind of confirming the rest. But what I do really like is that you take different approaches and then you just converge toward an answer that seems to show something consistent. But of course, any of these models has a number of limitations in terms, and